Welcome to Altera's Building Bootloader for Altera SoC's online training. In this training, we will explore the process of generating the necessary pieces for the bootloading stages for an Altera SoC Stratix 10 and Agilex 5 and 7 SoC FPGAs. We assume that you already have a basic understanding of the SoC architecture and the basics of the boot flow. I recommend that you view the prerequisite online trainings prior to this one, indicated in the resources section of this presentation. Let's get started. By the end of this training, you should be able to fully understand the functionality of the first and second stage bootloaders and be able to build, generate, and compile the bootloader for your device. Here's the agenda for the training. We will start with an introduction to building a bootloader. Then we will discuss the boot flows currently supported for Altera SoC FPGAs and provide an example of the flow for building bootloaders. Lastly, we'll explore some advanced topics. Altera SoC FPGAs use a bootloader to load and run the end-user application on the hard processor system. The end-user application may be a simple bare metal application or a complex operating system like the Linux operating system. When an SoC device boots up, a piece of software called the boot ROM is first run. All configuration and boot source interfaces are connected to the Secure Device Manager. The SDM determines and enforces the security level on the device, ensuring the bit stream, which includes the HPS first stage bootloader, originated from a trusted source. The boot ROM software has limited functionality, and the bootloader functions as a bridge between the boot ROM and the end-user application. Some of the limitations of the boot ROM are: it needs to fit in the on-chip RAM, so it has to be small. This is why, in some cases, you have two stages to boot. It is very expensive to change, so it must be robust. It does not know how the system was configured, so it cannot bring up everything at runtime. It can be as simple or complex as needed. Some functions range from configuring the clocks to network access. When booting the device from a power-on reset, you can choose between two different methods of booting through VMCell pins, which are hardware pins that indicate the booting configuration. Altera SoC FPGAs combine an FPGA with a hard processor system that can boot an operating system such as Linux OS or Zephyr RTOS. You can choose from two options for configuration. FPGA Configuration First Mode. When you select the FPGA first option, the SDM fully configures the FPGA, then configures the HPS SDRAM pins, loads the HPS first stage bootloader, and takes the HPS out of reset. HPS Boot First Mode. When you select the HPS first option, the SDM first configures the HPS SDRAM pins, loads the HPS FSBL, and takes the HPS out of reset. Then the HPS configures the FPGA I/O and FPGA fabric later. In previous slides, we discussed the Secure Device Manager and how it performs critical system tasks, such as managing device configuration and security. The SDM is also capable of performing services requested by HPS. The communication between HPS and SDM consists of commands and responses, which are managed using the HPS mailbox. The SDM always boots first and is responsible for locating and securely loading the configuration bit stream. The configuration bit stream includes the HPS FSBL, which the SDM copies to the HPS and releases the HPS from reset. The HPS is responsible for securing subsequent boot stages and may use services from the SDM to assist in HPS secure boot. Finally, the SDM also controls access to HPS debug. Here's a look at various typical boot stages and how the stages for the bootloader fit in the whole flow. For newer families, the bootloader is the SSBL, which will then load the OS and application or bare metal application. The boot process has fewer stages because the on-chip RAM is bigger and can accommodate the smaller bootloader of the newer families. The first stage bootloader is the first boot stage for the HPS. In FPGA configuration first mode, the SDM extracts and loads the FSBL into the on-chip RAM of the HPS. The SDM releases the HPS from reset after the FPGA has entered user mode. After the HPS exits reset, it uses the FSBL hardware handoff file to set up the clocks, HPS dedicated IOs and peripherals. Typically, the FSBL loads the SSBL into hard processor system SDRAM and passes control to the SSBL. The SSBL typically enables more advanced peripherals, such as Ethernet, and supports command line interface. In HPS first boot mode, the SDM, HPS, and HPS EMIF clocks must be running stable and set at the correct frequency before you begin any part of the configuration sequence. Finally, the SDM also controls access to HPS debug. Altera provides several resources to retrieve the first and second stage bootloaders for the device families. The Altera GitHub repository provides sources for the first and second stage bootloaders from U-Boot or ARM trusted firmware. You can also find the Linux OS and Zephyr RTOS sources to work with an embedded OS and build the whole software flow. The Yocto project also provides a way to have an initial version of the whole flow and necessary pieces for booting once the flash device is chosen to boot. Go to the latest Rocket Board's Golden System reference design for all the Altera devices for the whole flow of building bootloader and binaries. The Altera GitHub repository provides more information on Agilex SoC FPGA booting flow as described in the GSRD. To always have the latest information, go to our rocketboards.org and GitHub repositories provided in the links in the resources sections. The first stage bootloader is the first boot stage for the HPS, stored in QSPI. In FPGA configuration first mode, the SDM extracts and loads the FSBL into the on-chip RAM of the HPS. The SDM releases the HPS from reset after the FPGA has entered user mode. The FSBL loads the SSBL into HPS SDRAM and passes control to the SSBL. You can create the FSBL from one of the following sources provided by Altera in GitHub repositories. U-Boot Secondary Program Loader, ARM Trusted Firmware. One of the main functionalities of the SSBL is to perform HPS initialization for IOs, clocks, and peripherals that the HPS is configured to use. The second stage bootloader can be stored in NAND, SD/eMMC, or QSPI. The SSBL is a required component for all SoC applications on all SoC families. It must be compiled for all use scenarios. These are some of the second stage bootloader features. The HPS initialization includes configuring the IOs needed by each of the enabled HPS peripherals and setting the IO muxes so the appropriate pins are routed to the appropriate components. The SSBL also configures the clocks as specified in Platform Designer inside Quartus Prime software. These include the main processor clock, the interconnect clock, the clocks used by the various flash components, and the enabled peripherals in the HPS. The SSBL will also verify and copy the next stage software into the SDRAM and passes control to it. You can optionally perform FPGA core and I/O configuration during the SSBL stage. The SSBL copies the FPGA configuration files from one of the following sources to the HPS SDRAM: HPS Flash, SDM Flash, external host via the HPS Ethernet, for example, TFTP. After the SSBL copies the FPGA configuration files to the HPS SDRAM, the SSBL can initiate a configuration request to the SDM to begin the configuration process. Let's move on to the boot flows supported. Also known as ATF, ARM Trusted Firmware is software for implementing secure world software for ARM Cortex architectures. It includes firmware used as part of the booting flow as bootloader stages. Some of the interface standards implemented are the Power State Coordination Interface and the Secure Monitor Call. For more information, visit the ARM Trusted Firmware resources provided in the Resources section of this presentation. Free booting flows are supported to Linux OS or Zephyr from U-Boot or ARM Trusted Firmware. Let's take a look in detail at each one of the options. The execution level for ARM Trusted Firmware goes from exception levels EL3 to EL0, describing the convention recommended. Low-level firmware is EL3, hypervisor EL2, and EL1 is the operating system. BL31 is resident runtime firmware. The steps for the boot flow are: 1. The configuration management firmware running on the SDM loads the FSBL, which is U-Boot SBL, into HPS on-chip RAM and then brings the HPS boot core out from reset. 2. The U-Boot SBL loads the SSBL, which is ATFBL31 and U-Boot proper, into DDR. 3. The U-Boot SBL jumps to the ATFBL31. 4. The ATFBL31 sets up the GIC EL3 environment and initializes the PSCI services. 5. The ATFBL31 jumps to the U-Boot proper. 6. The U-Boot proper loads the Linux OS into the DDR. 7. The U-Boot jumps to the Linux OS. ATFBL2 is the first stage bootloader in this case. The booting stages are: 1. The configuration management firmware running on the SDM loads the FSBL, which is ATFBL2, into HPS on-chip RAM and then bring the HPS boot core out from reset. 2. The ATFBL2 loads the SSBL and OS, which is ATFBL31 and Linux OS, into DDR. 3. The ATFBL2 jumps to ATFBL31. 4. The ATFBL31 sets up the GIC EL3 environment and initializes the PSCI services. 5. The ATFBL31 jumps to the Linux OS. The booting steps for this boot flow are: 1. The configuration management firmware running on the SDM loads the FSBL, which is ATFBL2, into HPS on-chip RAM and then bring the HPS boot core out from reset. 2. The ATFBL2 loads the SSBL and OS, which is ATFBL31 and Zephyr RTOS, into DDR. 3. The ATFBL2 jumps to ATFBL31. 4. The ATFBL31 sets up the GIC EL3 environment and initializes the PSCI services. 5. The ATFBL31 jumps to the Zephyr RTOS. A fit image, also known as flattened image tree, is created from a .its file, image tree source, which has a similar structure to a regular device tree. The fit image could also be generated from a .dtsi file. The .its file describes how the fit image is conformed, defining the software pieces that will be part of the image. Unlike a regular device tree, the .its file also defines configurations. Each configuration defines the set of software items that will be used to launch a software item in a subsequent boot stage. For example, U-Boot SBL launches U-Boot or U-Boot launches Linux. Here we can see the boot flow with single image. These are the steps. S1. U-Boot SBL reads the board ID. S2. U-Boot SPL tries to find U-Boot.itb in the boot flash devices in order SD card, USB, and NAND. U-Boot SPL compares the appended board ID string with the description name in each of the fit configurations available in the fit file to determine which configuration is appropriate for this board. S3. In case of a match, The U-Boot SPL identifies the software items needed to launch U-Boot from the matching configuration and obtains their address in the FIT file. S4. The U-Boot SPL launches U-Boot with the software components identified. U-Boot SPL uses the board ID to determine the configuration that identifies the boot images of the software components that will be used when launching U-Boot, ATF, U-Boot, and FTT. U-Boot obtains the board ID and sets this in the environment variable. These are the necessary files to build the .itb file. The current build flow creates a single boot image, which is able to boot in different board configurations. It is the bootloader's job to apply these settings, and the process of the bootloader receiving these settings is called the hardware-to-software handoff. For Stratix 10 SoCs, Agilex 7 SoCs, and Agilex 5 SoCs, the handoff information is part of the FPGA configuration bit stream. The handoff includes also information on the FSBL. The primary method of entering or changing the handoff information is by editing them in the Quartus Prime Software Platform Designer project. In addition to the handoff information, the bootloaders also have various settings that the user can select through the following methods. Editing the bootloader source code. Editing the bootloader device tree when a device tree is used. This is an example of booting from SD card. The pieces produced by the build of the bootloaders and compilation of Quartus Prime project provide the necessary files to build an image and append the FSBL to a KeySpy image. On the left, we can see the KeySpy image file.jik with the combination of a .sof file produced from Quartus Prime compilation plus the FSBL from the U-Boot compilation or Yocto build. Then on the right, you can see the files for ARM trusted firmware, the .itb file from the single image boot flow with the second stage bootloader, device tree, and the board configuration. To know in detail about the different pieces of software, go to the latest version of the Golden System reference design for each device and family in Rocketboards or GitHub. Some of the tools needed to generate all the pieces for booting and building the bootloader for each stage are Quartus Prime software with Quartus Programmer. This will help generate the KeySpy image and then program the FPGA. The toolchain in the Linux OS terminal for building the software flow includes U-Boot and ARM trusted firmware. The sources from these two repositories maintained by Altera for each device provide the necessary files to build first and second stage bootloaders. Here you can see how the repository is being cloned and built to merge with the config file for a customized configuration. Now, let's move on to a couple of examples for building bootloader for Altera SoC FPGAs. This is an example of the whole flow for building all the binaries from the Golden System reference design. This example is for booting with an SD card, but you can also find the flows and instructions for booting from KeySpy, NAND, etc. After the files are generated from the Quartus Prime project compilation, the .sof file is used to create RBF, if needed, and .jik file for KeySpy image using Quartus Programmer. Then, to build U-Boot and ARM trusted firmware files indicated in the small table, compile and build using step-by-step instructions or a Yocto build flow. This will generate the list of files needed for booting, including an image and root file system. ARM trusted firmware is necessary in order to build the FIT image file as indicated in the table. Here is the generic flow needed to create a bootloader. The repositories for retrieving the versions for each device from U-Boot and ARM trusted firmware are provided as part of the GitHub sites maintained by Altera. Some of the user options include enabling or disabling features needed for a custom design or building specific drivers. Those additional configurations are provided as parameters for the drivers through the device tree files. This can all be achieved by a make tool, as seen in the diagram. As mentioned, the Quartus software project, including Platform Designer and Quartus Prime Programmer with the GHRD, is a good way to start. The HPS bootloader source code can be from U-boot or ARM trusted firmware, as described in the supported flows. Now that we see how the bootloader generation flow works for Altera SoCs, let's talk about some advanced topics that include bootloader generation command tools and debugging the boot flow. Here are some command line tools to use when building all of the pieces for the boot flow. To use Quartus Prime software tools from the Linux OS terminal, the tools need to be set up in the path. This points to the installation directory for Quartus Prime software. This will allow you to build the design using make from the Linux OS terminal and produce a .sof file. Then, the path and environment setup are done to work with the toolchain. Use the make command indicated in the slide to build ARM trusted firmware and produce the file for building U-boot. The commands to build U-boot are used as part of the whole compile to build single-image boot files, modifying the config files. By building the defconfig file with the make command, the default configuration and single-image configuration are combined to create the output files. To generate the JIC file and write the image to QSPI, use the last two sets of commands from Quartus software tools. To debug the Agilex SoC FPGA boot flow, several conditions might impact the system, such as reset and hardware configuration settings. Some examples of the effect of signals on booting and configuration have to do with reset and the inconfig signal. For more information, take a look at the Hard Processor System Booting User Guide link provided in the resources. Some debugging configurations can be done through Quartus Prime software and Platform Designer options. The watchdog timer can be configured in the IP parameters inside Platform Designer. This watchdog is active until the second stage bootloader indicates it has started correctly and taken control of the exception vectors. The timeout is configurable at the FSBL source. Inside Quartus software, you can configure the debug access port to use the HPS or SDM pins. This configuration allows the HPS JTAG port to be connected to HPS pins, SDM pins, or disabled. It is typically connected to SDM pins, so a single JTAG connection covers both SDM and HPS. You can debug the bootloader using ARMDS for Altera SoC FPGA. For that, you need a JTAG connection, enabling the HPS debug access port to be accessible through either the SDM or HPS pins, seen in the previous slide. ARM Development Studio is an Eclipse-based IDE where you can set hardware and software breakpoints and run scripts, among other functions, for the debug environment. Visit the resource link provided to learn about the capabilities of ARMDS, licensing, and documentation. RISC-free is Ashling's Eclipse C and C++ Development Toolkit, CDT, based Integrated Development Environment, IDE, for Altera FPGAs, ARM-based HPS, and RISC-V-based Neos 5 processors. The RISC-free IDE provides a complete, seamless environment for C and C++ software development and Intel Simix simulator integration for hardware simulation and debugging. Learn more about Ashling RISC-free IDE in the user guide resources from this presentation. In the GitHub repositories for the GSRD, you will find a tool for building a boot disk with partitions from the script provided. Here, we see an example of a disk with two partitions and its formats to build an output image file for an SD card. The FAT32 partition normally includes the U-boot files, Linux kernel, and Linux device tree, while the X3 partition is for the Linux file system. This table shows an example of the files on each partition for Agilex SoC FPGA's boot disk. The flow for producing each file can be found in the GSRD documentation for each family device and different booting devices. This training described how to generate the bootloader necessary files. You can use the Yocto flow for developing the rest of the pieces for the boot disk layout or build each set of files individually. Visit Rocketboards and GitHub for more information on the most recent flows and information on how to work with your device. This concludes the online training. Let's summarize what we've talked about. We started the training with an introduction to building a bootloader and then a review of the boot flows. Then we covered an example of build for Agilex 5 SoC FPGAs. Finally, we discussed advanced topics such as command line options, debugging the boot flow, and some boot definitions. Here are some additional resources regarding our SoC products. Please consult the appropriate device handbooks for more information on the devices and hardware components. We also offer several free online trainings that I would encourage you to take. These include the SoC Hardware Overview Training and the SoC Hardware and Software Design Flow Training. The Altera training team is always looking to improve our material. To do this, a survey will be emailed to your registration email address. We welcome any feedback you may have. Thank you very much for attending this online training. Best of luck with all of your designs.